We're asked to solve for the change in pH when we add 0.01 moles of sodium hydroxide to a liter of a buffered solution that's 0.5 molar acetic acid and 0.5 molar sodium acetate. For this example problem, we will assume no change in volume when we add this many moles of sodium hydroxide. So we can think of adding just a certain number of grams of sodium hydroxide. Sodium hydroxide all by itself is actually a solid. So add a mass that is equivalent to 0.01 moles. The first step is then to determine the initial pH. We are going to focus on this equilibrium reaction, the Ka equilibrium reaction. So we will assume that as this reaction occurs, this will decrease by x, this will increase by x, but as mentioned, we'll employ assumptions 2 and 3, as well as assumption number 1 when we carry out our calculation. So we'll take these values, we'll plug them into the Ka expression. The acetate concentration is 0.5 molar, the hydronium we don't know, and the acetic acid is 0.5. We rearrange, solve for x, and then take the negative log to get a pH of 4.74. So that's the initial concentration, the initial pH of this buffer solution before we have added any sodium hydroxide to it. The second step then is to figure out what happens when we add the sodium hydroxide to the solution. Well, the reaction that will occur will be the hydroxide of sodium hydroxide reacting with the weak acid in the buffer solution, acetic acid, producing some additional acetate. So for every mole of sodium hydroxide we add, we will decrease the amount of acetic acid by that amount and increase the amount of acetate by that amount. This reaction, if you look at closely, and your textbook also mentions this, is actually the reverse of the Kb reaction. So the reverse of the Kb reaction does not occur to a very large extent. So the Kb reaction, which is the reverse of this, does not occur to a very large extent. So this reaction as written would have a K value of 1 over Kb, which would be a very large K value. So the point being, we can assume this reaction goes to completion. Why is that important? Well, it's important so that we know that when we add 1 mole of this, we decrease this by 1 mole and increase this by 1 mole. Again, assuming the reaction goes to completion. Well, we're not adding 1 mole, we're adding 0.01 moles. So we're going to decrease the acetic acid number of moles by 0.01 moles. The initial moles of acetic acid will be the molarity of the acetic acid in the buffer multiplied by the volume. So this is initial moles acetic acid. We'll then subtract off the moles of sodium hydroxide that we added and divide by the new volume. Well, the volume didn't change, it's still 1 liter. This is now the new concentration of acetic acid. However, when we add sodium hydroxide, 1 mole of this will create 1 mole of acetate. So we've added 0.01 moles of sodium hydroxide, so we're going to increase the moles of acetate by 0.01 moles. Where the initial moles was 0.5, the initial concentration, multiplied by 1 liter, the initial volume. We then, after addition, divide by the new volume, which is 1 liter because we're assuming the volume didn't change. We now have the new concentration of acetate. And as you would expect, when you add a base, you should decrease the moles of acid and increase the moles of conjugate base in solution. So to solve for the new pH, we now have these concentrations. Again, we could assume a small change, but we always ignore that change. So we can take these initial concentrations, plug them into our Ka expression, solve for hydronium, just as we did before. Hydronium in this time is 1.7 times 10 to the negative 5, and our pH didn't really change much at all. It's now 4.76. So the change in pH is going to be final pH minus initial pH. Always remember that. Change in pH will be final pH minus initial pH. In this case, we get a positive pH change. That's because pH increased. If we get a negative pH change, then pH would have decreased. We always get a positive pH change when we add a base, because pH increases when we add base, but we will get a negative pH change when we add an acid, which I'll show you here in the next example. So this change in pH was very, very small, 0.02 pH units, by just adding 0.01 moles of sodium hydroxide. If you remember from the last lecture, the change in pH when 0.01 moles of sodium hydroxide was added to an unbuffered solution, water, was 5 pH units. So the buffer has done a really good job in decreasing the change in pH.